Welcome. In this work, we present LACOPE, a low-latency framework for joint pitch estimation and speech enhancement. Speech enhancement is performed using a traditional real-valued mask and a comp filter to enhance the periodic parts of speech. In contrast to previous work, our comp filter is applied in frequency domain, which has several advantages that I will cover in the next slides. Let's look at our framework. Starting with a noisy audio signal X, we compute pitch features similar to what PYIN is doing, and this is done in a latency-constrained fashion. Furthermore, we compute a spectrogram, which then both feed into the neural network. The DNN estimates real-valued gains, a voice probability estimate, as well as a pitch estimate. Now the gains are multiplied to this noisy spectrogram, so we already have an enhanced spectrogram which we can feed into our frequency domain comp filter module. In the end, we transform the signal back to time domain using a synthesis filter bank. This is our neural network. We have two separate encoders for the spectrogram features and for the difference function pitch features. These are both based on time-aligned convolutions, so they don't introduce any more latency. Then this is both feed into several GRUs, and on the decoder side we have our estimated gains, the pitch and the voice probability. Now when we look at the comp filter, in contrast to previous work which applied the comp filter on the noisy audio signal, we apply the comp filter in frequency domain. This has two advantages. First, for our comp filter we already have the enhanced spectrogram, capital X hat. Then, similarly to the time domain version, we add a delayed version based on the pitch period t. Now to compensate the lower sampling rate in frequency domain, we apply a phase correction factor, which depends on the center frequency of each frequency bin and the pitch period t. Now when we look at the performance, we can see that even for 0 milliseconds look ahead, we get a reasonable pitch accuracy. And for look ahead of 20 milliseconds, we outperform related work like CREPE. And the strength of our framework really shines when we have periodic noises like engine noise in this example. While other algorithms adapt to the engine noise, our algorithm only adapts to the pitch periodics, which allows to remove at least some part of the noise between the harmonics. Thank you for your attention.